students, welcome to episode 3. So we'll start here, episode 3. So in the last class we talked about what is a PDE, right? Now in this class we'll talk about some examples of PDE examples, okay? It is very important to understand this side and at least to be able to identify. So first PDE that I will mention is this. Okay, here alpha is a constant. Now this PDE is known as heat equation. And as you can see, there is only one direction here, x or x1. So this is called heat equation in one direction, one directional heat equation. Okay. There could be more example. For example, I just want to write. So okay. So just to give you an idea, if this is a heat equation in one direction, then what could be the heat equation in three directions? Okay. So sorry, let me change the color. Okay, here. So the direction. Hold on. Okay. In that case, you can. Okay. All right. So you see, you have u as a dependent variable and x, y, z as a independent variable. So here you have one dependent variable and multiple independent variables. Okay. In that case, you need to use partial differentiation or partial derivative, and using partial derivative, you can you get to analyze the trend of u in three different equations. So three different three different directions. I want to discuss more on this partial derivative equation, but I am thinking that I will not be able to discuss the main things that I want to discuss about ODE, because the focus is ODE. But this is very exciting. So you may ask, like, why do I need all three, right? In what world we need all three, right? Usually, in application, in our world is a 3D world. So this is a very good example, like, because this is a heat equation in 3D, okay? And our world is a 3D world. So everything that we do that are confined in these three directions, okay, x, y, and z. So let's think about this. I'll just give you an example, okay? So since we're going to talk about this, so let's think about this. So let's say this is a room, maybe, okay, we can see this is a room. There's a window, I guess. All right, etc. And just imagine this is a room, and there's a heater here. Okay, I'm gonna change the color so just to make sure. So that heater is radiating heat. So if this is you identify as x, y, and z directions. So that's how you cover all three directions in this room. So if you wanna understand the trend of heat transfer, okay, in at any point, okay, then you need to use this heat equation. Okay, so this is a very important equation in thermal, not only in thermal science, but also in many different fields where you know the properties or particles, they follow the heat equation. There is another interesting equation that is called as Laplace equations. In the Laplace equations, so we just discussed homogeneous and non-homogeneous equation in the previous video. So you remember, if the solution is set to 0, then it's a homogeneous equation, and if it is not set to 0, then it's a non-homogeneous equation. So according to that definition, you already understand this is a non-homogeneous equation, right? It's a non-homogeneous equation. However, what if you set this to 0, like this solution? So let me write the same equation. Okay. And setting this to 0, then this is a homogeneous equation, but the name of this equation is Laplace equation. Okay. And there are also applications regarding this equation as well. So we'll stop here. We'll stop talking about these equations so far, PDE and ODE and their classification. But right now, I'll just discuss some example, like our motivating examples. Okay, let's get on. Let's discuss one motivating example. Why would you learn ODE or PDE? What makes you learn ODE, PDE? Like I said, college professors, if they are from mathematics background, they wouldn't consider teaching you a whole lot of applications of differential equations. They will just show you how to solve a differential equations. And if you are like me from Bangladesh, like I'm from Bangladesh, I did my undergrad in Bangladesh. It's a different scenario. So in countries like Bangladesh and other countries, I think it's the same in the US too. That ODE and PDE, they are taught by professors from math department, and they do not care about engineering examples. And in Bangladesh, we had to solve some, I don't know, like some pathetic books written by some, writers who just only cared about how to solve a problem without understanding why am I doing it. Okay, so let's think about a motivating example. So let's discuss a motivating example for differential equation. So let's say this is a single story shear building which is under excitation of an earthquake. So there's a earthquake taking place. If you don't understand what I'm saying earth, but because of my accent, this is what I'm saying. Okay, so this building is subject to earthquake. Now this shear building, so this is a shear building that I'm talking about. Now this shear building, this building here, okay, I'm just highlighting the whole thing. This shear building, it consists of a rigid girder of mass m supported by columns of combined stiffness k. All right, so here this image is very much exaggerated, but what we are trying to say that, let me just delete this thing. Okay, that ruined my whole picture, but anyway, okay. Here, this is a girder. Okay, this girder is supported by these columns. These are the columns. Okay, these are the columns, and they have a stiffness of k. So the vibration of the girder, how can be described as like xt. So what would be the relative displacement between the girder and the ground? So this is the ground, as you can see. Okay, hold on. This is the ground. Okay, so the relative displacement is relative displacement is yt is equals to xt minus x naught t. So xt is the final movement from the reference. This is a reference, final movement from the reference, and this is the initial movement from the reference. So this is what I am looking for, the relative displacement. All right, and this relative displacement is governed by this equation, which is a differential equation. So I will not show you how to derive this equation right now, but I'm just going to show you. Okay, so this is acceleration, this is the velocity, and that's the displacement, and by combining all of them you get the governing equation. Okay, the governing equation of the relative displacement between the girder and the ground. Okay, so this is another example. There could be other examples too, but I prefer that I'd like to move forward and start solving differential equations at this point, and learn about the applications as we solve them. So I look forward to the future lessons where I start talking about how to solve a differential equation. First, before we get on with solving a differential equation, we also need to identify what type of differential equation is this. So I'll just do a very simple differential equation solution, and before we talk about differential equation solution, we need to talk about two things. There are general solutions of a differential equation, and there are particular solutions for a differential equation. Now, what is the difference between two? In general solution, equation is not defined. Sometimes the equation is not defined by any boundary. In that case, if there is no boundary or initial condition, in that case, you cannot generate any particular solution. Because if you remember, if you do integration, like let's just say integration of x dx, right? So it will produce x squared by 2 plus c. So because of this arbitrary constant, if you don't know the boundary conditions or initial conditions of your differential equation, you will not be able to identify this arbitrary constant. Okay, in that case you will not be able to get to the particular solution. So particular solution involves understanding and knowing the initial and boundary condition of your equation. Okay, so before, I think we can in the future video we can talk about how to solve a differential equation.